Poster number 4, effect of long baffles on forced convection heat transfer over multiple heated blocks.
Ladies and gentlemen, dear colleagues, assistants, welcome. Before presenting my paper, I'd like to introduce myself. I'm Hamza from Algeria and I have a new PhD degree from the University of Medea. Ladies and gentlemen, I have the honor to present in front of you my paper, which has as title Effect of Long Baffles on Forced Convection Heat Transfer over Multiple Heat Blocks. The plan adopted for this presentation is the following. We begin with an introduction, then we introduce the objective of the study. After we pass to the physical model and mathematical formulation, followed by the used resolution method. Before finishing, we will introduce the results, and finally we finish with a conclusion. Introduction. The forced natural or mixed convection heat transfer has a very diverse application in different fields such as heat exchangers, solar collectors, energy storage, and cooling of electronic systems. In the last decades, the electronic field saw a huge development by the increase of its performance and processing speed. The new development is accompanied with more heat generation that affect the electronic chips integration in the real math of electronic systems. For this reason, thermal engineers keep enhancing and developing new cooling methods to prevent the electronic chips from the failure resulting from the heat generation. We pass to the objective of this study. As shown in figure 1, the stagnation fluid as a warm air vortex after each heat block reduces the heat transfer in the rear face of each block. To avoid this problem, we will use long baffles as in the figure 2. The aim is to perform a comparison between the cases with and without long baffles and see the effect of long baffles on the flow structure and heat transfer. The physical model and mathematical formulations. We start with the physical model. The configuration involved in this investigation are shown in figure 3. It consists of 2D channel containing 5 heat blocks with identical sizes. For the first configuration presented in the figure A, long baffles with constant length and thickness are fixed in the upper wall of the channel. The second configuration is investigated without long baffles for a comparative reason. And in both cases, a uniform heat flux is imposed at the bottom of each block, and the flow with a parabolic profile velocity is applied at the inlets. The following assumptions are made to simplify the equation of the physical phenomena and make the calculation easier and faster. The fluid is Newtonian, viscous, and incompressible. The flow is laminar. The flow is two-dimensional along x and y, and all physical properties are assumed to be constant and are evaluated at the reference temperature. The effect of the buoyancy is negligible, viscous dissipation is negligible, and the heat transfer variation is neglected. As a consequence, the mathematical equations of physical model in the non-dimensional form can be written as follows: the equation of mass, the equations of momentum in both directions x and y, and finally the equations of energy for fluid and solid phase. The partial differential equation developed previously require boundary conditions to be solved. So these conditions are detailed in the following table. The resolution of the equation that govern our physical phenomena require a numerical method that allow us to transform this differential equation into a system of linear algebraic equations before solving them. In this study, the finite volume method has been used. The ANSYS Fluent software are used to create our physical phenomena, and this choice is motivated by the fact that this software provides a very powerful tool for the creation of the model and the generation of the mesh. And most importantly, that this software allows a good resolution of the problem related to the forced convection in the laminar regime. The results are presented and showed as streamlines, which are a family of curves that are instantaneously tangent to the velocity vector of the flow. These show the direction in which a massless fluid element will travel at any point in time. B. Temperature contours, or more simply, isotherm lines. In a fictitious line that the temperature is constant alone. And finally, the Nusselt number. The Nusselt number is a dimensionless number used to characterize the heat transfer between a fluid and solid wall. It is defined as the following equation. The validity of the calculations is investigated by comparison with the work of Young and Vathey for Reynolds equal to 1000. As appeared in the figure, a great agreement is obtained and the maximum deviation is less than 3%. For the results analysis, we start with the streamlines. As appeared in the figure A, the streamlines goes forward in a smooth motion till they hit the first block and the baffle. The gaps between the baffle are filled with 3 recirculation zones, a big localized zone conducted by the main channel flow. This vortex approximately takes all the space between the baffles. The shear in the vicinity of the front and rear faces of each baffle lead to the creation of 2 other co-rotating vortices on both sides of the baffles. The long length of the baffle make the flow penetrate the gaps between blocks, which break the stagnation of the warm air stacked in this region, as detected for the case without baffles. Figure B. A moderate size vortex is shown above each block, horizontal face. Due to the sudden change in the flow passage section caused by the combined effect of the baffle and blocks, 2 superposed large vortices are formed in the backstream of the last baffle. These 2 vortices appear like a plug, reducing the main flow to a thin layer near the bottom wall. Unlike the case with long baffles, a moderate size vortex is detected after the last block. The isotherm contours are presented for both cases with and without baffle in this figure. As shown in this figure A, the presence of baffles generates a higher temperature gradient in the solid phase. All blocks are cooled regularly, and the temperature gradients in the solid appear very close to those in the fluid phase. For the case without baffles, figure B, the temperature increases through the blocks with the flow direction until achieving quite high value for the last block. The lowest temperature is captured on the upper corner of the front face, followed by the upper corner of the rear face, while the maximum temperature is recorded on the back lower corner. In terms of thermal file, it is clearly shown that the long baffles bring significant change to the isotherm shape in the solid and in the fluid phases. As appear, the temperature of the blocks is reduced with the long baffles. To show the effect of the baffles on the heat transfer, the main Nusselt number for the cases with and without long baffles are presented in this figure. As it can be seen, the heat transfer is increased with the baffles more than 3 times better than the case without long baffles at Reynolds equal 100. Moreover, the local Nusselt number value for the case with baffle at Reynolds equal to 100 are about 2 times much higher than the case without baffle at Reynolds equal to 1000. The improvement is due to the increase in the flow velocity over the blocks and the elimination of the warm circulation vortices after each vortex after each block. Finally, we conclude that the cavity is no more occupied. The cavities are no more occupied by the warm vortices, and the flow structure are changed. Concerning the temperature contours, the temperature in the solid and the fluid phases is decreased significantly compared to the case without long baffles. And for the heat transfer quantification, the enhancement exceeds 3.5 and about 2 times better than the cases without baffles for Reynolds equal to 100 and 1000 respectively. Thank you for your attention.